Hello everyone, welcome to this lecture of this course heat transfer. Today we will be discussing or we will be continuing the module that is heat exchanger. Okay. So earlier we have discussed the different classification of heat exchanger, then the design and analysis of the heat exchanger. Here we have seen the importance of LMTD and NTU in the design and analysis of the heat exchanger, different types of heat exchanger. So there, in case of parallel and counter flow, the formula for the LMTD, that is logarithmic mean temperature difference, and the formula for the NTU, that is number of transfer units, we have seen. We have discussed the derivation earlier. Now today we will be discussing different numericals for parallel and counter flow heat exchanger in terms of the NTU analysis. Okay. So let us start this lecture. Now, before discussing the numericals regarding the NTU analysis of heat exchanger, there is another terminology which is important for the design of the heat exchanger. Now, that terminology it is known as the pressure drop and pumping water, that is the pumping cost. So, how to determine that effective pumping cost or pumping power, and how it is related to the pressure drop in case of the heat exchanger design. So what happens while designing a heat exchanger, that is the size of the heat exchanger, it can be reduced by forcing the fluid through the heat exchanger at higher velocities. Now, if we force the fluid through the heat exchanger at higher velocity, in that case the overall heat transfer it will increase for the heat exchanger. But what happens then? Due to the higher velocity of the fluid through the heat exchanger, there will be a larger pressure drop and it results to a larger pumping cost. Now, the smaller diameter pipe for a given flow rate, it may involve less initial capital cost but definitely higher pumping costs for the life of the heat exchanger. Now we know that the pressure drop, that is for an incompressible fluid, it is delta P. It is proportional to the mass flow rate. Now mathematically it can be represented as delta P directly proportional to m dot, that is the mass flow rate square. So this delta P, it is the pressure drop of an incompressible fluid through the pipes, and mass m dot, it is the mass flow rate. So what is a compressible fluid or what is an incompressible fluid? All these things have been discussed earlier. Now, in order to pump fluid in a steady state, in that case the power requirement it is given by integration V dP. So it can be again represented as m dot by rho multiplied by delta P. So it is almost equal to mass flow rate cube. So that means we are getting one mathematical representation, that is power is almost equal to mass flow rate cube. So that means what? It indicates the power requirement, it is proportional to the cube of the mass flow rate of the fluid. Okay, so the power requirement in case of a heat exchanger, it is proportional to the cube of the mass flow rate of the fluid which is flowing through the heat exchanger. Now it may be further increased by dividing it by the pump efficiency. So that means we are getting that the pumping cost it increases greatly with higher velocities. That means when the fluid is flowing through the heat exchanger with higher velocities, in that case the pumping cost it is increases. Hence a compromise will have to be made between the larger overall heat transfer coefficient and corresponding velocities. So this thing we need to keep in mind while designing a heat exchanger. Now let us discuss the numericals. So the first numerical, what it says, that 16.5 kg per second of the product at 650 degrees centigrade, CP is given 3.55 kilojoule per kg degree centigrade, in a chemical plant are to be used to heat 20.5 kg per second of the incoming fluid from 100 degrees centigrade. So the CP is given 4.2 kilojoule per kg degree centigrade. Now, if the overall heat transfer coefficient is 0.95 kilowatt per meter square degree centigrade and the installed heat transfer surface is 44 meter square, we need to calculate the fluid outlet temperatures for the counter flow and parallel flow arrangements. So how to proceed here? How to find the fluid outlet temperature for the counter flow and parallel flow arrangement. So what are the things given in this question? That is the mass flow rate of the hot fluid, that is given 16.5 kg per second. The inlet temperature of the hot fluid, it is given 650 degrees centigrade. The specific heat of the hot fluid, it is given 3.55 kilojoule per kg degree centigrade. Now for the cold fluid, the mass flow rate, its inlet temperature and specific heat it is given, and the overall heat transfer coefficient is given 1.2 kilowatt per meter square degree centigrade, and the heat transfer surface area, it is given 44 meters square. So as we need to calculate the fluid outlet temperatures for the counter and parallel flow arrangement respectively, so let us start with the counter flow arrangement. Now, what is the thermal capacity of the hot fluid? In the derivation of this NTU, or the effectiveness, we have seen that the thermal capacity, that is Ch for the hot fluid, it is represented mathematically by mass flow rate of the hot fluid multiplied by the specific heat of the hot fluid. So the mass flow rate and specific heat for the hot fluid is given. So the thermal capacity of hot fluid, it is 58.6 kilowatt per Kelvin. Now in this similar manner, we can calculate the thermal capacity of the cold fluid. So that is m dot c multiplied by Cp, the specific heat in case of the cold fluid. So which we are getting as 86.1 kilowatt per Kelvin. And here we can see that the thermal capacity of the cold fluid, it is higher or greater than the thermal capacity of the hot fluid. So the cold fluid, it is the maximum fluid, whereas the hot fluid, it is the minimum fluid here. So that means C mean by C max, that is R, is the capacity ratio. It is actually 0.68 now, ratio of C mean by C max. So C mean, it is the thermal capacity of the hot fluid, and C max, it is the thermal capacity of the cold fluid based on the values that we have calculated here. Now, what is the value of the NTU, that is the number of transfer units? The formula is UA divided by C mean. So U is the overall heat transfer coefficient, which is given in this question. The heat transfer surface area, it is given 44, and the C mean, it is the thermal capacity of the hot fluid. As all the values are known to us, we can calculate the number of transfer unit, it is 0.71. Now the value of the effectiveness for this counter flow arrangement, it is mathematically represented as epsilon, this is equals to 1 minus e to the power minus NTU to 1 minus r divided by 1 minus r e to the power minus NTU 1 minus r. Now in this formula, if we put all the values, that is the NTU and R, that is capacity ratio, all the values are known to us, then we can easily calculate the value of this effectiveness. It is, we are getting a 0.443. Again, the formula for this effectiveness, it is also written as Ch multiplied by the temperature difference of the inlet and outlet for the hot fluid divided by C mean multiplied by the Th1 minus Tc1. Now because here the hot fluid is minimum, that means C mean, it is the Ch. That means the Ch can be cancelled here in the formula of this effectiveness. So the formula of the effectiveness, it is now Th1 minus Th2 divided by Th1 minus Tc1. Now in this formula, except the value of the Th2, that is the outlet temperature of the hot fluid, all the other values are known to us. So putting all the other values, we can calculate the outlet temperature of the hot fluid. It is coming as 406.35 degrees centigrade. Again, the effectiveness, this is represented as Cc multiplied by Tc2 minus Tc1 divided by C min multiplied by Th1 minus Tc1. So again, if we put all the values which are known to us, then we can easily calculate the outlet temperature of the cold fluid, that is we are getting as 265.8 degrees centigrade. So considering the counter flow arrangement, we have calculated the outlet temperature of the hot fluid and cold fluid. Now if we consider the parallel flow arrangement, in that case the formula for the effectiveness, it is actually 1 minus e to the power minus NTU into 1 plus R divided by 1 plus R. And here NTU and R, all the values are known to us, so the effectiveness can be calculated here as 0.415. Again, the other mathematical representation of this effectiveness, if we use here, that is Cc multiplied by Tc2 minus Tc1 divided by C min multiplied by Th1 minus Tc1. Now here, except the value of the Tc2, all the other values are known to us, so putting all the other values, we can calculate the outlet temperature of the cold fluid. It is coming as 255.4 degrees centigrade. Okay, so this is the procedure for the effectiveness NTU method, by which we have calculated the outlet temperature of the hot fluid and cold fluid in case of the parallel and counter flow arrangement. Let us move to the next page. The next question, it is given as two fluids A and B exchange heat in a counter current heat exchanger. Fluid A enters at 420 degrees centigrade and has a mass flow rate of 1 kg per second. Fluid B enters at 20 degrees centigrade and has a mass flow rate of 1 kg per second. The effectiveness of the heat exchanger, it is given as 75%. Now we need to determine the heat transfer rate and the exit temperature of the fluid B. The specific heat of the fluid A is given 1 kilojoule per kg Kelvin, and this specific heat of the fluid B, it is given 4 kilojoule per kg Kelvin. So in this numerical, we need to find two different things, that is the heat transfer rate, and the other thing, it is the exit temperature of the fluid B. Okay, so let us write the things or the values of the parameters which are given in this numerical. So TA1, it is the temperature of the fluid A at inlet. So that is the hot fluid. So it is given as temperature of the hot fluid at inlet. It is given 420 degrees centigrade. Mass flow rate of the hot fluid, it is given 1 kg per second. Mass flow rate of the cold fluid, it is also similar, that same, it is 1 kg per second. Now the inlet temperature of the cold fluid, that is the fluid B, it is given 20 degrees centigrade, and the effectiveness, it is given 0.75. Specific heat for the hot fluid, it is given 1 kilojoule per kg Kelvin, and specific heat for the cold fluid, it is given 4 kilojoule per kg Kelvin. Now to find the heat transfer rate Q, the formula for this Q, we can see here after 2 or 3 steps, that is epsilon, that is effectiveness, into C min multiplied by Th1 minus Tc1. So this is the formula for the Q of, that is heat transfer rate that we need to apply here. Effectiveness multiplied by C mean into Th1 minus Tc1. Now in this numerical, Th1 and Tc1, these are given, that is 420 and 20 degree centigrade. Effectiveness, it is also given, that is 0.75, and C mean. So this one we need to identify here. So first let us write the formula of the effectiveness, that is represented as Ch multiplied by Th1 minus Th2 divided by C mean multiplied by Th1 minus Tc1. Now here Ch, that is the heat capacity of the hot fluid, it is m dot h Cph, which are 1 for both the cases. So this is equals to 1, that is the heat capacity of the hot fluid. So this is equals to C mean. So the effectiveness, this is equals to Th1 minus Th2 divided by Th1 minus Tc1. Now from this formula we can easily calculate the value of the Th2. So the value of the Th2, it is coming as 120 degrees centigrade. Now if we put the formula of the Q, that is the heat transfer rate, Q equals to epsilon C mean Th1 minus Tc1. So epsilon is given in the question, 0.75. C mean, this one we have calculated. So that is the capacity, heat capacity of the hot fluid, which is equals to 1. And Th1 and Tc1, these two things are given in this numerical. So ultimately we are getting the value of the heat transfer rate, it is 300 kilojoule. So this is the answer of the first part of this numerical, that is the value of the heat transfer rate, it is 300 kilojoule. Now for the second part of this numerical, we need to find the exit temperature of the fluid B, that is the exit temperature of the cold fluid. So for that we can use this formula, that is the heat gained by the cold fluid, Q equals to m dot C Cpc multiplied by Tc2 minus Tc1. So Q we have calculated for the first part of this numerical, that is 300, m dot C multiplied by Cpc. So m dot C is given in this numerical, that is the mass flow rate of the cold fluid, it is 1. Specific heat for the cold fluid, it is given as 4, and Tc2, this one actually we need to find here, and Tc1, it was the inlet temperature of the cold fluid, it was given 20 degrees centigrade. So putting all the other values in this equation, we can easily calculate the value of the outlet temperature of the cold fluid, so which we are getting as 95 degrees centigrade. So this is the procedure by which we have calculated the heat transfer rate for this counterflow heat exchanger and the exit temperature of the cold fluid. So for that we have used the concept of the, or the formula of the effectiveness, then the formula of the heat transfer rate in terms of effectiveness and heat capacity. And after that, for the second part of this numerical, we have used the formula of this heat transfer rate, but in terms of the mass flow rate of the cold fluid and specific heat of the cold fluid. So let us move to the next numerical. A counterflow heat exchanger is to heat air entering at 400 degrees centigrade with a flow rate of 6 kg per second by the exhaust gas entering at 800 degrees centigrade with a flow rate of 4 kg per second. The overall heat transfer coefficient, it is given as 100 watt per meter square Kelvin, and the outlet temperature of the air, it is given as 551.5 degrees centigrade. The specific heat at constant pressure for both air and exhaust gas can be taken as 1100 joule per kg Kelvin. Now we need to calculate the heat transfer area and the number of transfer unit, it is NTU. Now the diagram, it is given here for the counterflow heat exchanger. So here we can see that theta 1 it is Th1 minus Tc2 and theta 2 it is Th2 minus Tc1. So this concept is known to us from the LMTD. Now m dot c, that is the mass flow rate of the cold fluid, it is given 6 kg per second. Inlet temperature of the cold fluid, it is given 400 degrees centigrade. Outlet temperature of the cold fluid, it is given 551.5 degrees centigrade. The inlet temperature of the hot fluid, it is given 800 degrees centigrade. M dot H 4 kg per second. Overall transfer coefficient 100 watt per meter square Kelvin. And the specific heat for the hot and cold fluid, these are same, and this value is 1100 joule per kg Kelvin. Now the heat capacity for the cold fluid, this is actually the formula, that is m dot c multiplied by Cpc. So this mass flow rate and the specific heat for the cold fluid, these are given in this numerical. So we are getting the heat capacity for the cold fluid, this is 6600, and in this similar manner we can also calculate the heat capacity of the hot fluid, that is we are getting as 4400. Now here you can see that the heat capacity of the hot fluid, it is lesser, or it is smaller than the heat capacity of the cold fluid. That means here now the C mean is the minimum heat capacity, it is now the heat capacity for the hot fluid, it is 4400. Now we can write this relation, that is the heat transfer to cold air. This is actually heat transfer from the hot gases. And the heat loss equals to heat gain for the two different fluids. So if we write the formula for this case, so Q equals to m dot c Cp multiplied by Tc2 minus Tc1. This is equals to m dot h Cph multiplied by Th1 minus Th2. Now here if we put the values which are known to us, then we can calculate the value of the outlet temperature of the hot fluid, which we are getting as 572.75 degrees centigrade. Now for the first part of this numerical, we need to calculate the heat transfer area needed. So for that we need to use the concept of the LMTD. So the formula for the heat transfer rate in case of the LMTD, that is Q equals to UA theta m. Now this theta m, it is the LMTD. In case of this counterflow heat exchanger, the formula of LMTD equals to theta 1 minus theta 2 divided by ln theta 1 by theta 2. Now as all the values are known to us, we can easily calculate the LMTD, which we are getting as 208.33 degrees centigrade. Now substituting the values in the earlier equation, we are getting the area of this heat transfer is 48 meters square. Now for the second part of this numerical, we need to calculate the NTU, that is the number of transfer unit. So the formula of the NTU, it is UA divided by C mean. Now the overall transfer coefficient U is given in this numerical 100. The heat transfer area we have calculated for the first part of this numerical, which is 48, and the C mean, which is the heat capacity of the hot fluid that we have calculated earlier, which is 4400. If you put all these values in the formula of the NTU, then we can calculate the value of the NTU as 1.09. So this is the procedure to solve this numerical. This type of numerical, these are not very easy and not very complex also, so sufficient practice is required to solve such numericals based on the LMTD and NTU, because we need to remember some critical formulas to solve such numericals. Let us discuss the next numerical. A chemical having specific heat of 3.3 kilojoule per kg Kelvin flowing at the rate of 20,000 kg per hour enters a parallel flow heat exchanger at 120 degrees centigrade. The flow rate of cooling water is 50,000 kg per hour with an inlet temperature of 20 degrees centigrade. The heat transfer area is 10 meters square and the overall heat transfer coefficient is 1050 watt per meter square Kelvin. So these are the things given in this numerical. Now we need to find the effectiveness, it is epsilon of the heat parallel flow heat exchanger, and the outlet temperature of water and chemical. The specific heat for water, it is given 4.186 kilojoule per kg Kelvin. So this is a default value, so this may not be given in the question also, and we need to remember. So this thing was already told while discussing the numerical of the LMTD. Now let us first write what are the things given in this numerical. The specific heat of the hot fluid, it is 3.3 kilojoule per kg Kelvin. Mass flow rate of the hot fluid 5.56 kg per second. TH1 120 degree centigrade. Mass flow rate of the cold fluid 13.89 kg per second. Specific heat of the cold fluid 4.186 kilojoule per kg Kelvin. TC1 20 degree centigrade. Area 10 meters square and overall heat transfer coefficient 1050. So first we need to find the effectiveness of the heat exchanger. So for that we need to first find the heat capacity, because this terminology is there in the formula of the heat exchanger. So the heat capacity for the hot fluid, it is actually the multiplication of m dot h into Cph. So 5.56 multiplied by 3.3, so it is 18.35. Now the heat capacity for the cold fluid, it is m dot c multiplied by Cpc. It is 13.89 multiplied by 4.186, which is 58.14. So here you can see that the heat capacity for the hot fluid, it is smaller than the heat capacity of the cold fluid. That means C mean here it is CH. Now the heat lost by the hot fluid, this is equals to heat gained by the cold fluid. So if we write the equation for this relation, then if we put all the values, then after some steps we can calculate the value of TH2 and TC2. Now for the second part we need to calculate the NTU. So this is here in this numerical. The formula of the NTU, it is UA by divided by C mean. So overall transfer coefficient, it is given in this numerical. Area is also known. And the C mean, it is now the CH. So it is 18.35. So we have calculated this one here in the earlier page. So we can calculate the formula of the NTU, it is 0.572. Now the effectiveness, if we write the formula of the effectiveness for this parallel flow heat exchanger, then it is 1 minus e to the power minus NTU into 1 plus R divided by 1 plus R. And here R, it is the capacity ratio, so it is C mean divided by C max. So R can be calculated 0.316. Now effectiveness, it can be calculated by putting all the values in the formula of this epsilon. So we are getting the value of the effectiveness, this is equals to 0.402. Now from the equation 1, if we want to calculate the outlet temperatures of the hot and cold fluid, that is TC2 and TH2, then we need to use Another mathematical representation of this effectiveness, that is Ch multiplied by Th1 minus Tc2 divided by C min multiplied by Th1 minus Tc1. So the value of the effectiveness is already calculated for the first part of this numerical. Then Ch, that is the heat capacity of the hot fluid, it is actually here the C min, because this value of the Ch, it is lesser than the Cc, that is the heat capacity of the cold fluid. So Ch is C min here. So we can cancel out the Ch and C min. So we are left with the rest part in this formula. So from that part we can easily calculate the value of the outlet temperature of the hot fluid, which we are getting here is 79.8 degrees centigrade. Now if we put these values in the earlier equation 1, then from that part we can again calculate the outlet temperature of the cold fluid, which we are getting as 32.7 degrees centigrade. So this is the procedure to solve such numerical. So let us discuss the next numerical. A parallel flow heat exchanger has hot and cold water streams running through it, and it has the following data. So some data are given here, like m dot h, m dot c, then cph, cpc, and th1, th2, tc1. So that means we need to calculate the tc2 here, and the overall individual heat transfer coefficient on both the sides 60 watt per meter square degree centigrade. We need to calculate the following: the area of the heat exchanger, that is capital A, and the exit temperature of the hot and cold fluid if hot water flow rate is double. So another condition is given here if the hot water flow rate is double. Now for the first part of the numerical, we need to calculate the area of the heat exchanger. So first we have used that concept, that is heat lost by the hot fluid, this is equals to heat gained by the cold fluid. So from this formula we have calculated, that is the outlet temperature of the cold fluid, that is 33 degrees centigrade. If you want to calculate the LMTD, so the LMTD formula for this parallel flow heat exchanger is equals to theta 1 minus theta 2 divided by ln theta 1 by theta 2. Now as all the values are known to us, then we can easily calculate the value of LMTD, which is 28.8 degrees centigrade. Now the overall heat transfer coefficient, it can be represented here. This is 1 by U, this is equals to 1 by Hi plus 1 by Ho. Now here if we put the values which are given, it is both are same and the value is 60, which was given in this numerical. So we can easily calculate the value of overall transfer coefficient, which is coming as 30 watt per meter square degree centigrade. Now Q can be represented mathematically like this in terms of the hot fluid parameters, that is m dot h cph into th1 minus th2. So this is written in terms of the LMTD as UA theta m. Now from this equation we can calculate the area of the heat exchanger, which we are getting as 0.0161 meters square. Okay, so this is the procedure to solve this numerical, and for the second part of this numerical, the exit temperature of hot and cold fluid, we need to calculate if the hot water flow rate, it is doubled. Now the hot water flow rate, it was earlier given m dot h, it is 10 kg per minute. Now if it is doubled with m dot h value, it is given, it is now 20. So now considering this value and following the same procedure, we can calculate the exit temperature of hot and cold fluid, that is Th2 and Tc2. So these are the procedure where we have used the concept of LMTD and NTU. For parallel and counter flow heat exchanger, we have used the concept of the effectiveness to solve this numerical. Again, we have used the concept of the heat exchanger analysis, where we have used the concept that is heat gained by the cold fluid is equals to heat lost by the hot fluid. So, and we have used the formula of the capacity ratio. So various formula regarding the heat exchanger in terms of LMTD and NTU we have used here to solve different numericals of this heat exchanger. So this is the end for this lecture.